Two image models, same prompt, a cat sitting in a window. You want to know which one is better, so you do the obvious thing. You look for the right answer to compare against. And then you stop because there is no right answer. There is no single correct cat picture. The whole point of a generator is to invent something new, something that was never in the training set, so there is nothing to check it against. Think about how strange that is. Every other kind of machine learning has an answer key. A spam filter is right or wrong. A translation has a reference. A model that reads an X-ray has a doctor's label. You score them by counting how often they match the truth. But truth here is a thing that does not exist. So how do you put a number on a picture that is supposed to be new? You cannot improve what you cannot measure, and it turns out measuring this is genuinely hard. Every automatic quality score people use for AI images is a leaky proxy. Today is about what each one really measures, and exactly how each one lies. Because reading a leaderboard honestly is impossible until you know that. Here is the move that unlocks everything. If you cannot compare one fake picture to one real picture, stop comparing pictures. Compare collections. Forget any single cat. Instead, take thousands of real cat photos and thousands the model invented and ask one question about the two piles as a whole. Does the pile of fakes look like it was drawn from the same place as the pile of reals? That word place is doing real work. Last season we said a generator is secretly learning a probability distribution, the hidden shape of what real data looks like, and then drawing fresh samples from it. So good generation has two parts that pull against each other. Fidelity, every sample should look real. And diversity, the samples together should spread out and cover the full variety of real cats, not just paint the same ginger tabby 1,000 times. A good metric has to reward both at once. And the only way to see both is to stop staring at individual images and step back to look at the entire cloud. This is exactly what the most famous image metric does. It is called the Frechet Inception Distance, FID for short, and for nearly a decade it has been the number papers live and die by. The mechanism is simpler than the name. First, you cannot compare raw pixels, so you push every image, real and fake, through a frozen vision network, an old image classifier called Inception, and grab the numbers from one inner layer. That turns each picture into a couple of thousand features, a point in a high-dimensional space. Now you have your two clouds, the blue real one and the orange fake one. Then comes the clever shortcut. Instead of comparing the clouds point by point, which is impossible at this scale, you summarize each cloud by a simple shape. You fit a smooth blob to it, an ellipse, described by just its center and its spread. FID is almost literally the distance between those two ellipses. One number. As the generator gets better, the orange ellipse slides over and settles onto the blue one, and the number drops towards 0. Lower is better. 0 would mean the two clouds are statistically the same. Now the twist, and it is the heart of this episode. Comparing whole clouds has a blind spot built right into it. Watch what happens if a model cheats in a particularly sneaky way. Suppose it does not really invent new cats at all. It has secretly memorized a wide spread of training photos and just replays them, lightly retouched. To your eye, this is a disaster. No creativity, basically a photocopier. But think about where those copied points land. They land right on top of real points, scattered across the whole real cloud. So the fake cloud still has the same center and the same spread as the real one. The two ellipses match almost perfectly, FID drops towards 0, and the leaderboard says, beautiful. The metric literally cannot tell a model that learned the distribution from one that just Xeroxed the training set, because copying the reals is the one way to look exactly like the reals. One careful caveat, because the real world is messier. This blind spot is the idealized case, a model that copies the full variety of the training set. Most memorization in practice is lazier than that, replaying the same few images over and over, and that loses diversity, which actually shrinks the spread and pushes FID up, not down. So FID is not totally blind to memorization. It is blind in exactly one direction, the perfect diversity copy, where a thief who steals everything evenly looks identical to an honest model. Catching that needs a different dedicated test, one that hunts for near duplicates of training images. And this is not the only crack. The exact FID number depends on fiddly details, how you resize the images, the image format, how many samples you used. So two papers quoting FID often are not even measuring the same thing. Worse, that old inception network was trained to recognize 1,000 everyday objects, one per photo. It was never built to judge the rich, many-object scenes today's models paint, so it is increasingly the wrong ruler. Newer versions swap in stronger vision backbones and drop the smooth blob assumption, and they track human opinion better, but the field has not agreed on a single replacement yet. So treat FID as a useful smoke alarm, never as the truth. One older cousin of FID you will still see quoted is the inception score. It runs your fakes through that same classifier and rewards images that look sharply like one clear object, and that, across the batch, span many different objects. Its giveaway weakness is that it never looks at a single real image. It only checks the generator against itself, so it cannot tell whether your cats actually resemble real cats, only that they look like confident somethings. Useful history, not a verdict. But notice the deeper thing that FID and its cousins never even ask. They check whether your fakes look like real images in general. They do not check whether your image matches the prompt you typed. Ask for a red cube on top of a blue sphere and get a gorgeous, photorealistic blue cube on a red sphere, and FID can be perfectly happy, because both are plausible images of cubes and spheres. So we need a second, totally different kind of metric, one for prompt alignment. The classic one is the CLIP score. CLIP is a model that learned to place an image and a caption into the same space, near each other when they agree. So you embed your generated image, embed the prompt, and measure how close they land. Higher means better agreement in theory. In practice, it has a famous weakness. CLIP reads text almost like a bag of words, a loose handful of concepts with the grammar shaken out. So the horse is eating the grass, and the grass is eating the horse score about the same. Counting, negation, left versus right, a cube on top of a sphere, all the relationships that make a sentence mean something, are exactly where it is weakest. A high CLIP score does not mean the picture got the prompt right. It mostly means the right ingredients are somewhere in the frame. So the field got more clever about alignment, and the fixes are genuinely smart. Instead of one fuzzy similarity score, you decompose the prompt into checkable facts and verify them one by one. One approach, Geneval, runs an object detector over the image, the same kind of model that draws boxes around things and asks concrete questions. Is there a cube? Is it blue? Is it on top of the sphere? Are there exactly two of them? Each is a yes or no you can actually score, and when it fails you can see precisely why. Another approach, VQA score, leans on a vision language model, the kind you can ask questions about a picture, and simply asks, does this image show a red cube on a blue sphere, then reads how confidently it answers yes. These compositional checks line up with human judgment far better than the old bag-of-words score, especially on counting and spatial relationships. They are not perfect. The detector or the questioner can be wrong, but the lesson is the pattern. The way you beat a metric that is too crude is to break the question into pieces a machine can honestly verify. So far we have a metric for realism and metrics for matching the prompt. But there is a third thing humans care about that neither captures: taste. Lighting, composition, the 1,000 little things that make one correct image feel beautiful and another feel cheap. You cannot write a rule for that, so the field did the obvious thing. It learned it. Show people millions of pairs of images and let them click which they prefer, then train a model to predict those clicks. That is a reward model. Names you might see are image reward, pick score, HPSV2, and they are basically a learned stand-in for human taste, a number that says how much a person would probably like this. Useful, but there is a trap hiding here, and it is sharp. These same taste models are now used not just to judge generators but to train them. You tune your generator to score higher on the reward model, which means you are optimizing the exact thing you are also grading with. And anything you optimize hard enough, you eventually start to game. The generator learns the reward model's quirks, the little visual tics it happens to love, and racks up a great score while a real person shrugs. You have improved the number without improving the picture. Which is why, when you want the real verdict, you go back to the only judge that cannot be a proxy for itself. Actual humans voting. The top-line ranking for image models in 2026 works like a chess ladder. Show a person 2 images from the same prompt, hide which model made each, and ask which is better. Winner gains rating points, loser drops them, and after enough blind votes every model lands on a single number and a low score. If this sounds familiar, it should. Last season, when we asked whether language model benchmarks lie, we met a law called Goodhart's, that the moment a measure becomes a target, it stops being a good measure. Same law, new medium. So even this gold standard has to be read carefully. First, it measures preference, not correctness. People reliably vote for the prettier, glossier image, even when the other one actually followed the prompt better, so the latter quietly rewards style over substance. Second, it has documented biases. The big-name models get shown far more often, which stabilizes their rank, while the headline number is usually printed with no error bar at all, so a 1 or 2 point lead can be statistical noise dressed up as a winner. And every name and number on that board is a snapshot of this month. So use the arena as the best single signal we have, and never as the last word. And everything so far was the easy case, still images. Now add time. To judge a video, you need all of this and more, because a clip can look gorgeous frame by frame and still be broken. The face flickers between shots. An object morphs as the camera pans. The motion stutters or nothing moves at all. So video evaluation splits the question into many separate scores. Things like, does the same character stay the same person across the whole clip? Is the motion smooth? Is there flickering? Does anything actually happen? Does it follow the prompt? A suite like VBench tracks more than a dozen of these at once, leaning on vision models to check whether a subject keeps its identity from frame to frame. Audio is the same story in another sense. A generated song or voice gets a panel of proxies too, and in the end, like images, the real verdict is people sitting down and listening. The pattern never changes. As generators move into harder media, no single number can carry the weight, and the honest answer is always a panel of imperfect measures plus human ears and eyes. So step back and look at the whole shape of it. A generator has no answer key, so we built a tower of proxies, and the real skill is knowing exactly how high up that tower you can trust. FID, the distribution distance, catches gross realism and diversity, but goes blind to a model that memorizes. Alignment scores check that the prompt's ingredients showed up, and the smarter ones check that they are in the right relationships, but a checker can be fooled. Reward models bottle human taste until you optimize against them and they start lying back to you. And blind human votes are the best we have, yet they reward the pretty over the faithful and come with no error bars. There is no single number for good, and there never will be. Anyone who shows you one is selling something. What actually works is a panel, a distribution metric, an alignment metric, a taste metric, and real human votes, each covering the other's blind spots, every one of them hedged. And here is the thing that keeps this honest forever. The metrics are always a step behind the models they judge, because the vision networks doing the grading are usually weaker than the generators they grade. So the next time you see a chart that says this model is the best, you now know the only useful question. Best on which proxy, and how does that one lie? That question is the whole literacy. Hold on to it.